James Clerk Maxwell was born into a world that was just beginning to grasp the deeper laws of science, yet he himself was destined to push that understanding far beyond what anyone of his age could imagine. His story begins on June 13, 1831, in the city of Edinburgh, Scotland, but his formative years were largely shaped in the quiet countryside of his family's estate at Glenlair. Surrounded by rolling hills, serene landscapes, and the vast Scottish skies, Maxwell grew up in an environment that would leave an indelible mark on his imagination. Unlike many children who pass through their early years absorbed in simple games, Maxwell was drawn to patterns, structures, and questions about the world that others rarely considered. From an unusually young age, he began to show signs that his mind worked in a way that was both curious and deeply analytical. His mother, Frances K. Maxwell, played an important role in nurturing his early education. A woman of intellect and determination, she encouraged her son to explore, to question, and to discover. She instilled in him a love of reading and a discipline for learning, guiding his first steps into a world of knowledge. She believed that education was not something confined to a classroom, but something that could be found in every stone, every leaf, and every star. With her guidance, James was introduced to scripture, literature, and the sciences before most children his age could even read fluently. This early foundation became a compass for his intellectual journey. Tragically, Maxwell's mother died when he was only 8 years old, a devastating loss that left a void in his young life. Yet her influence had already taken root, and James carried with him her encouragement to keep seeking truth. His father, John Clerk Maxwell, though not a scientist himself, supported James's growing curiosity. John was an attentive and caring figure who made sure his son had the tools and opportunities to pursue his interests. The rural estate of Glenlair became a vast laboratory for young James, where fields, streams, and the endless sky served as both inspiration and playground. He would wander for hours observing natural patterns, tracing shapes in the water, and sketching intricate diagrams of objects he saw. This natural environment helped sharpen the young boy's observational powers, and it gave him the sense that nature itself was a grand book written in codes, waiting to be deciphered. What set Maxwell apart was not simply his curiosity, but the intensity and depth with which he pursued questions. As a child, he was captivated by geometrical shapes and the idea of symmetry. By the age of 14, he had already produced a remarkable scientific paper on the description of oval curves, which explored mathematical methods of defining complex curves. This was not the work of a typical schoolboy, but of a mind that was already searching for hidden order beneath the surface of reality. His classmates often teased him for his relentless focus and unusual habits, but Maxwell was undeterred. He had entered a world of discovery that few of his peers could even comprehend. The Scotland of Maxwell's youth was a place alive with intellectual activity. Edinburgh was often referred to as the Athens of the North, a hub of philosophy, science, and literature. Ideas were flowing through the city in lectures, publications, and societies, and though Maxwell was raised in the countryside, he was not far from this intellectual ferment. When he began formal schooling in Edinburgh, he was exposed to new influences that sharpened his mind further. Though shy and awkward at first, his brilliance soon became impossible to ignore. Teachers and scholars recognized that this boy was no ordinary student. The young Maxwell's passion extended beyond books and mathematics. He was equally enchanted by the physical world around him. He built mechanical models, experimented with light and color using simple tools, and devised ingenious ways to test ideas. Every new observation became a puzzle for him to solve, and every puzzle was another doorway into the mysteries of nature. He was not content with simply memorizing knowledge. He wanted to understand why things were the way they were. Even before he had the formal training of a scientist, Maxwell was already thinking like one, framing questions that would later form the backbone of his revolutionary theories. His early life was not without its challenges. He was often misunderstood by his classmates, who mocked him for his rural accent and eccentric mannerisms. To them, Maxwell seemed odd, a boy who preferred equations and experiments over games and social chatter. But those same eccentricities were the signs of a mind operating on a different plane, one that could look at a spinning top or a ray of sunlight and see in them the principles of motion, energy, and light. What others dismissed as quirks were, in fact, the seeds of genius. By the time he entered Edinburgh Academy, Maxwell had already developed habits that would stay with him for life. He carried notebooks filled with sketches, diagrams, and questions. He collected observations of everything from the play of light on glass to the motion of water currents. He even explored the nature of colors by mixing pigments and analyzing their combinations. Long before he became known for his work on electromagnetic theory, Maxwell was experimenting with the very phenomena that would later lead him to groundbreaking discoveries. One of the most remarkable things about Maxwell's early years was the way he combined imagination with logic. Many children dream, and many others analyze, but Maxwell managed to fuse the two into a powerful tool of insight. He could imagine possibilities beyond what was visible, and then he could test those possibilities with careful reasoning and experiment. This rare combination allowed him to see connections that others could not. In the ripples of water, he sensed mathematical order. In the spread of colors, he envisioned hidden laws of light. In the spinning of objects, he glimpsed patterns of motion that would later influence his scientific thinking. This ability to unify imagination and analysis would define his career. In his youth, it simply made him seem extraordinary, a boy with unusual hobbies and remarkable talents. Yet to history, it would mark him as one of the greatest scientific minds ever born. The discipline of his early life was also remarkable. While many children relied heavily on structured teaching, Maxwell often pushed beyond the boundaries of the curriculum. He pursued questions independently, sometimes outpacing the resources available to him. His father would help by acquiring books and instruments, ensuring that James's curiosity never ran into a dead end. At home in Glenlair, James would turn household objects into scientific tools, finding ways to learn even when formal education was absent. This self-driven exploration built resilience in his mind and a confidence that he could tackle questions others left unexplored. The influence of Scottish culture cannot be overlooked in shaping Maxwell's early passion for learning. Scotland in the early 19th century placed high value on education and intellectual pursuit. With universities and academies flourishing, and public discourse alive with debate, Maxwell grew up in a culture that admired thinkers and innovators. He was not an anomaly in a land uninterested in science. He was a star rising in a country that valued the light of knowledge. This supportive environment, combined with his innate talent, created the perfect conditions for a young genius to flourish. What made Maxwell's childhood particularly striking was his relationship with the unseen. While many children are captivated by what they can see and touch, Maxwell's mind was already drawn to forces and patterns invisible to the naked eye. He was fascinated by the way light refracted through glass, how magnets influenced iron filings, and how heat changed the behavior of objects. He wanted to go beyond appearances, to uncover the hidden framework holding the universe together. This desire to understand the invisible would later define his most important contributions to science. The story of Maxwell's early life is not simply a tale of a gifted child, but of a relentless spirit that refused to stop questioning. At every stage, he was driven by a hunger to know more, to see deeper, to connect what others thought unconnected. His childhood was not only the preparation for his later discoveries, it was the foundation of his genius, the training ground where his curiosity was sharpened into insight. The later years of Maxwell's childhood deepened the patterns that had already begun to emerge. His insatiable curiosity, his ability to see beyond the obvious, and his relentless need to question the world around him continued to set him apart from his peers. At Edinburgh Academy, though often teased and isolated socially, Maxwell found within himself an unshakable commitment to learning. His teachers, who initially struggled to understand his unique approach to problems, gradually came to see that this boy was not simply unusual, but extraordinary. He had a way of looking at problems that revealed structures no one else could perceive. Where another student might see only a shape drawn on the blackboard, Maxwell saw an entire field of relationships, equations, and principles hidden within that shape. By his early teens, Maxwell was already thinking about the great themes of nature in a way that most adults could not. One of the first glimpses of his genius came when he worked on his paper on the description of oval curves, completed at the age of just 14. To his teachers, it was astonishing that such a young boy could construct a mathematical study of curves that displayed such originality. This was not merely a clever school exercise, it was evidence of a mind capable of producing knowledge, not just consuming it. His work hinted at a gift for unifying abstract mathematics with the concrete realities of geometry, a skill that would later blossom in his profound understanding of physics. What makes Maxwell's early life so compelling is the way he transformed personal struggles into strengths. His awkwardness, his sense of isolation, and his difficulty in fitting in did not break him. Rather, they seemed to drive him deeper into the world of thought. The playground taunts that labeled him as eccentric only sharpened his determination to focus on what truly mattered to him. Instead of withdrawing completely, he turned to nature and the life of the mind as his true companions. He found endless fascination in water ripples, spinning tops, and the play of light on surfaces. To most, these were ordinary sights. To Maxwell, they were messages from the universe, signals of deeper truths waiting to be understood. As he grew older, his explorations became more ambitious. He began constructing experiments that tested the ideas he carried in his mind. With simple tools and an inventive spirit, he would mimic the behavior of light and color, experimenting with reflections and refractions. He observed the dynamics of spinning objects and drew careful conclusions about motion. He developed ways of analyzing phenomena that others ignored. This early creativity foreshadowed his later ability to take invisible forces like electricity and magnetism and render them visible through mathematics. Maxwell's youth coincided with a remarkable period in Scottish intellectual life. The country was still basking in the glow of the Scottish Enlightenment, and institutions such as Edinburgh University stood at the forefront of European thought. The culture celebrated knowledge, and scientific societies flourished. For young Maxwell, this was fertile ground. His entry into the broader world of education exposed him to a stream of ideas that fueled his growing ambition. He was no longer a boy lost in his own curiosity. He was becoming a thinker who could absorb the best of his culture and push it further. During these years, his father remained a quiet but steady supporter. Though not a scientist, James Clerk Maxwell provided his son with the encouragement and resources needed to keep pursuing his questions. If James needed books, John acquired them. If James wished to explore experiments, John supported him. Their bond was not only familial but intellectual in its own way, as the father recognized in his son something rare and worth nurturing. Without that support, Maxwell's genius might have faced unnecessary obstacles. With it, he was free to keep expanding his horizons. One of the defining traits of Maxwell's early intellectual character was his obsession with seeing connections. He could not accept isolated facts. He wanted to know how they fit into a larger picture. When he studied geometry, he looked not only at shapes, but at the principles that linked them. When he played with colors, he thought about how the human eye perceived them, and how those perceptions might be explained scientifically. When he examined physical objects, he sought the hidden laws governing their motion. This hunger for unity and coherence would become the foundation of his mature scientific vision, but it was already evident in his youth. There is something almost poetic about the way Maxwell engaged with the world. For him, science was not a mechanical exercise but a dialogue with nature. The countryside of Glenlair was not just a backdrop to his childhood. It was a living laboratory, a canvas on which he practiced his early observations. The patterns in the bark of trees, the symmetry of a flower, the shimmering play of sunlight, all of these became invitations to inquiry. It was as though he could hear whispers in the natural world, urging him to uncover the secrets written into its fabric. In those quiet Scottish landscapes, a boy was training himself to become one of the greatest scientists in history. The early life of Maxwell also reflected a kind of resilience and independence that would later define his career. He learned early on not to rely too heavily on the approval of others. Mocked by classmates, sometimes misunderstood by adults, he found confidence within himself and in the pursuit of truth. This independence of thought gave him the courage to challenge accepted wisdom later in life, to propose theories that seemed implausible to others but were ultimately proven correct. That same independence, born out of childhood solitude, became a cornerstone of his genius. As adolescence gave way to youth, Maxwell's talent only grew more luminous. At a time when most students were grappling with basic studies, he was exploring the boundaries of mathematics and science. He absorbed knowledge voraciously, but more importantly, he applied it in creative and original ways. His notebooks from this period reveal not only an abundance of sketches and calculations, but also the spark of ideas that hinted at his future breakthroughs. Every observation, no matter how small, could become the seed of a theory. Every question, no matter how ordinary, could open into a grand investigation. The tragedy of losing his mother at such a young age continued to shadow his early years, but it also gave him a seriousness unusual for a boy of his age. Life had already shown him its fragility, and in that awareness, he seemed to find a greater determination to use his time well. He did not waste his intellect on trivialities. Every day was an opportunity to discover, to understand, to push further. That intensity, rooted in early loss and early promise, propelled him forward with a sense of purpose. In reflecting on Maxwell's youth, one can see how perfectly it prepared him for the monumental achievements to come. His childhood fascination with light foreshadowed his later unification of light with electricity and magnetism. His youthful obsession with geometry anticipated his ability to construct elegant mathematical frameworks. His playful experiments with colors pointed toward his later discoveries in optics and photography. His endless pursuit of hidden connections laid the groundwork for his most famous achievement, the realization that the forces of electricity and magnetism were not separate phenomena, but two faces of the same fundamental law. The boy who once roamed the fields of Glenlair sketching patterns in the water was the same man who would later write the equations that redefined physics. The continuity is remarkable. His early life was not merely a prelude but a microcosm of his genius. All the traits that defined Maxwell the scientist, curiosity, imagination, rigor, independence, and unity of vision, were already present in Maxwell the boy. The narrative of James Clerk Maxwell's early years is a reminder that genius is not an accident of adulthood, but often the flowering of seeds planted in childhood. In Maxwell's case, those seeds were curiosity about the unseen, love of patterns, and an unwavering belief that the universe was intelligible. He carried these seeds with him from the countryside of Scotland into the classrooms of Edinburgh, and eventually into the great halls of scientific discovery. They grew with him, matured with him, and ultimately made him the man behind modern physics. It is easy to look at Maxwell's equations and see only the brilliance of the adult scientist, but the roots of those equations stretch back to the boy who traced the curves of light and saw in them something more than beauty. They stretch back to the child who asked questions others never thought to ask, and who never stopped searching for answers. His early life was the foundation upon which modern physics was built, a foundation laid not in laboratories or universities alone, but in the simple observations of a child who looked at the world and wondered endlessly about its mysteries. The greatness of James Clerk Maxwell did not begin with his published works or his academic achievements. It began in the mind of a boy who refused to let go of curiosity. That is the true significance of his early years. They were not just the beginning of a life, but the beginning of an era in science. From Glenlair to Edinburgh, from sketches of curves to the equations of electromagnetism, Maxwell's path was clear. He was destined to reveal the hidden harmony of the universe. His early life reminds us that behind every discovery lies a story of childhood wonder, of questions asked in innocence but pursued with passion. For Maxwell, that wonder never faded. It grew into a light that illuminated physics for all generations to come. Electricity and magnetism had long fascinated scientists before James Clerk Maxwell entered the scene, but the knowledge of these forces was fragmented, scattered across experiments, theories, and partial understandings. By the time Maxwell began his work in the mid-19th century, great minds like Michael Faraday, André Marie Ampère, and Charles Augustin de Coulomb had already uncovered essential pieces of the puzzle. They had shown that electric charges exert forces, that electric currents produce magnetic fields, and that magnets themselves follow predictable laws. Yet there was no unifying principle, no single framework that could bind all these discoveries together. It was into this unfinished landscape that James Clerk Maxwell stepped, bringing with him a rare combination of mathematical brilliance and deep physical intuition. Maxwell's pioneering contributions to electricity and magnetism were not the work of a sudden inspiration, but the result of years of careful thought, study, and synthesis. From his earliest years, he had been captivated by invisible forces, the phenomena that could not be seen but whose effects were undeniable. Light refracting through glass, magnetic fields shaping patterns in iron filings, the spark of static electricity, all of these hinted at forces beyond direct perception. Maxwell was drawn to the unseen, to the challenge of capturing what the eye could not grasp. Unlike many who were content to describe phenomena, he sought to explain them in terms of underlying principles and mathematical relationships. Michael Faraday had provided one of the most important foundations for Maxwell's work. Faraday, with little formal mathematical training, had relied on intuition and experiment to describe the nature of electric and magnetic forces. He developed the concept of lines of force, visualizing electric and magnetic fields as patterns stretching through space. Though Faraday's vision was revolutionary, it remained largely qualitative, a powerful picture, but not a precise mathematical theory. Many physicists admired Faraday's genius, but regarded his ideas as incomplete. Maxwell, however, recognized in Faraday's concept of fields the seeds of something profound. He saw that these lines of force could be expressed in mathematical terms, that the vague became clear when described with equations. In this marriage of Faraday's intuition with Maxwell's mathematics lay the birth of modern electromagnetic theory. Maxwell's journey into electricity and magnetism began with his desire to unify. He was never satisfied with separate laws describing isolated phenomena. For him, the electric and the magnetic were not two distinct realms, but parts of a greater whole waiting to be revealed. His early studies focused on translating Faraday's lines of force into mathematics. Where Faraday spoke of invisible patterns, Maxwell constructed differential equations to describe them. The elegance of mathematics allowed Maxwell to see what Faraday had intuited, that the electric field and the magnetic field were intimately linked, each influencing the other in ways previously unrecognized. One of Maxwell's first major steps was to examine the existing laws of electromagnetism and reformulate them. The laws of Coulomb, Ampère, and Gauss each described aspects of electric or magnetic behavior. Coulomb's law explained the attraction and repulsion of charges. Ampère's law described how currents generate magnetic fields. Gauss's law explained how electric charges create fields that spread outward. Each was valuable but incomplete. Maxwell's genius lay in weaving them together into a coherent structure. Through his mathematical skill, he began to reshape these laws into a system that would ultimately reveal their deeper unity. A crucial insight came when Maxwell introduced the concept of the displacement current. Ampere's law described how a current creates a magnetic field, but there were situations where this law seemed incomplete. For instance, when a capacitor was charging, an electric current flowed onto one plate and off the other, yet between the plates there was no actual current of moving charges. Ampere's law predicted no magnetic effect in that space, but experiments suggested otherwise. Maxwell resolved this paradox by proposing that a changing electric field could act just like a current, producing a magnetic field. This displacement current was an imaginative leap, but it was also a logical necessity to preserve the consistency of the equations. With this single addition, Maxwell completed the symmetry of electromagnetism, linking changing electric fields to magnetic effects. From this insight emerged a revolutionary realization. Maxwell's equations, when combined, predicted that electric and magnetic fields could sustain each other, propagating through space in waves. A changing electric field produces a magnetic field, and a changing magnetic field produces an electric field, creating a self-sustaining oscillation. The mathematics revealed that these electromagnetic waves travel at a finite speed. When Maxwell calculated this speed, he discovered that it matched the measured speed of light. The conclusion was astonishing. Light itself is an electromagnetic wave. With this, Maxwell had unified optics with electricity and magnetism, showing that these seemingly separate domains were manifestations of a single force. This discovery cannot be overstated in its importance. Before Maxwell, light was understood as a wave, thanks to the work of Thomas Young and Augustin Jane Fresnel, but its nature was a mystery. What kind of wave was it? What was oscillating? The electromagnetic theory of light gave the answer. Light was the oscillation of electric and magnetic fields rippling through space. Suddenly, the entire electromagnetic spectrum lay open to discovery. If visible light was one form of electromagnetic radiation, then there must be others, perhaps with longer or shorter wavelengths. Maxwell's theory predicted the existence of radio waves, microwaves, infrared, ultraviolet, X-rays, and beyond, forms of radiation that would only be discovered decades later, but that would transform technology and human life. Maxwell's work did not emerge in isolation. He was deeply engaged with the scientific community of his time, presenting his findings to the Royal Society and corresponding with fellow scientists. Yet his equations were so far ahead of their time that many of his contemporaries struggled to grasp their significance. The elegance of the mathematics was evident, but the physical implications were staggering. It took years before experimental proof, in the hands of Heinrich Hertz, confirmed the existence of electromagnetic waves. Only then did the world fully appreciate the scale of Maxwell's contribution. But even without immediate confirmation, Maxwell himself knew he had uncovered something monumental. In his 1865 paper, A Dynamical Theory of the Electromagnetic Field, he laid out his ideas with clarity and precision. He showed how electricity and magnetism could be described as fields permeating space, how their interactions produced waves, and how those waves were identical with light. It was a unification of breathtaking scope, comparable in its power and elegance to Newton's unification of celestial and terrestrial mechanics 2 centuries earlier. Maxwell's pioneering contributions extended beyond the equations themselves. He also provided physical models to help others grasp his concepts. He visualized the electromagnetic field in mechanical terms, imagining vortices and gears that illustrated the transmission of forces. While these models were later abandoned as unnecessary, they were crucial in helping his contemporaries accept the reality of the field. In an age still dominated by mechanical analogies, Maxwell's ability to blend abstract mathematics with visual metaphors made his theories more accessible. The true genius of Maxwell's contributions lay not only in solving existing problems, but in opening entirely new vistas of inquiry. His equations were not just explanations of known phenomena, they were predictions of phenomena yet unseen. The displacement current, the existence of electromagnetic waves, the unity of light and electromagnetism, all were bold extensions beyond the evidence of his day, yet all proved correct. Maxwell had given science not merely a description of the world, as it was known, but a roadmap for discoveries that would shape the 20th century. The impact of Maxwell's work on electricity and magnetism cannot be separated from its influence on later giants like Albert Einstein. Einstein often said that Maxwell's equations were the foundation upon which he built the theory of relativity. The constancy of the speed of light, a cornerstone of special relativity, was itself revealed by Maxwell's unification of light as an electromagnetic wave. Without Maxwell, the entire structure of modern physics would have lacked its most crucial pillar. In reflecting on Maxwell's pioneering contributions, it becomes clear that his genius was not merely in mathematics or physics alone, but in his vision of unity. He saw that the universe was not a collection of isolated forces, but a tapestry woven together by deep, underlying principles. His ability to take the fragments of knowledge scattered by his predecessors and weave them into a coherent whole is what makes him one of the greatest scientific minds in history. When Maxwell first published his electromagnetic theory, few could have imagined how profoundly it would transform the world. At the time, electricity and magnetism were intriguing curiosities studied in laboratories and lecture halls, yet far removed from daily life. Sparks from Leyden jars, the twitch of frog legs in Galvani's experiments, and the behavior of magnets fascinated scientists, but seemed to hold little practical use for ordinary people. Maxwell, however, had revealed that these forces were not isolated oddities, but fundamental aspects of nature, bound together in a deep and elegant harmony. What appeared to many as invisible and mysterious had been given a language, the precise, predictive, unifying mathematics of Maxwell's equations. The four equations that today bear Maxwell's name were not originally presented in the compact form familiar to modern students. They were spread across his writings, expressed in a more complex mathematical language. It was later, through the work of Oliver Heaviside and others, that Maxwell's insights were condensed into the beautiful quartet of equations we know. Yet even in their original form, the essence of Maxwell's vision shone through. Electric charges create fields, magnetic poles and currents create magnetic fields, changing magnetic fields induce electric effects, and changing electric fields create magnetic effects. Together, these principles formed a cycle of interaction that explained phenomena across scales, from sparks to sunlight. One of the most remarkable aspects of Maxwell's contribution was his ability to take Faraday's intuitive field concept and elevate it into a rigorous scientific theory. Faraday had drawn pictures of magnetic lines and electric curves, showing how forces seemed to radiate through space. To many, these were merely suggestive sketches, useful perhaps for visualizing experiments, but lacking in precision. Maxwell took those sketches and gave them mathematical form. In doing so, he transformed a metaphor into a law of nature. The invisible fields were no longer vague notions, they became measurable, calculable entities that obeyed strict equations. The idea of a field, an entity that could exist in empty space, carrying energy and momentum, was revolutionary. It replaced the older view of forces acting instantly at a distance with a new vision of interactions, mediated through fields that filled all of space. This shift was not merely academic. The recognition that fields themselves were physical realities reshaped physics from top to bottom. No longer was space an empty stage where forces acted from afar. Space itself became alive with structure, filled with invisible fields that governed the behavior of matter and energy. In this new vision, light was not a mystical substance or a mechanical vibration of some hidden medium, but a wave in the electromagnetic field. With one leap, Maxwell had given the universe a new substance, a new framework through which all interactions could be understood. Yet in Maxwell's time, the implications of his theory were not fully grasped. His great paper of 1865 laid out the mathematical theory of the electromagnetic field, but many of his contemporaries struggled to comprehend its physical meaning. It was abstract, far removed from the simple demonstrations of sparks and magnets that most scientists were accustomed to. For many, It remained a brilliant piece of mathematics, admired but not entirely believed. It would take Heinrich Hertz, 2 decades later, to prove Maxwell right beyond any doubt by generating and detecting electromagnetic waves in the laboratory. Only then did the scientific community realize that Maxwell had uncovered not only the nature of light, but also the existence of an entire unseen spectrum of radiation. When Hertz demonstrated radio waves, it was like unlocking a door that Maxwell had predicted but never walked through. Soon after, innovators like Guglielmo Marconi and Nikola Tesla harnessed these waves for communication, transforming Maxwell's abstract equations into the foundation of modern technology. The radio, the telegraph, the wireless, all were born from Maxwell's vision. What had begun as a search for unity among invisible forces became the seed of the communications revolution that would shrink the globe. But Maxwell's contribution was more than practical applications. He changed the way scientists thought about nature itself. His unification of electricity, magnetism, and light was one of the first great demonstrations of a principle that would come to dominate modern physics, that seemingly distinct forces are aspects of a deeper unity. Just as Newton had shown that the same laws govern apples falling and planets orbiting, Maxwell showed that the flicker of a spark and the glow of the sun were manifestations of the same fundamental field. This spirit of unification would inspire later generations of physicists in their quests to merge all the forces of nature into a single framework. The predictive power of Maxwell's theory extended far beyond his own time. His equations not only described existing phenomena, but also pointed to possibilities unknown in the 19th century. The concept of electromagnetic waves suggested that light was only a tiny part of a vast spectrum. Later discoveries of radio waves, microwaves, X-rays, and gamma rays confirmed this. Every modern technology that relies on these forms of radiation, from broadcasting and radar to medical imaging and satellites, traces its roots back to Maxwell's insight. Perhaps the most profound impact of Maxwell's work was on the foundations of physics itself. His equations, by predicting that electromagnetic waves travel at a constant speed, raised deep questions about the nature of space and time. If the speed of light was fixed, how could it remain the same for observers moving at different speeds? This paradox puzzled scientists until Albert Einstein resolved it with the theory of special relativity in 1905. Einstein himself acknowledged his debt to Maxwell, saying that the theory of electromagnetism was the most profound and fruitful change in physics since Newton. Maxwell had prepared the way for relativity by revealing the constancy of light's speed, embedding it into the structure of the equations themselves. Maxwell's work also laid the groundwork for quantum physics. The study of electromagnetic radiation eventually led to the discovery of the photon, the quantum particle of light. His field theory became the starting point for quantum electrodynamics, one of the most successful theories in all of science. Though Maxwell himself could not have imagined the quantum revolution, his unification of electricity and magnetism provided the essential stage on which that revolution would play out. In the human story of science, Maxwell's contributions to electricity and magnetism represent a turning point. Before him, physics was still deeply tied to mechanics, to gears and levers, to the motion of particles colliding like billiard balls. After him, physics became about fields, waves, and invisible structures that pervade the universe. He shifted the language of science from the tangible to the abstract, from the directly visible to the deeply conceptual. It was a leap that required imagination, courage, and faith in the power of mathematics to reveal truths beyond direct experience. Maxwell's genius was that he could see the invisible. He could take Faraday's lines of force, intangible and unmeasurable, and translate them into the rigorous symbols of calculus. He could imagine displacement currents where no charges flowed and still be confident enough to insist they must exist. He could calculate the speed of a wave that no one had ever seen and identify it with light itself. These were acts of audacity, of vision, and of deep trust in the unity of nature. His pioneering contributions remind us that science advances not only through careful observation, but also through leaps of imagination guided by logic. Maxwell did not simply record what was known, he ventured beyond, proposing what must be true for the laws to be consistent. In doing so, he reached truths that would only be confirmed decades later, but which today stand as cornerstones of physics. The story of Maxwell's work in electricity and magnetism is not just the story of equations, but the story of a worldview. It is the story of how humanity came to understand that the universe is woven together by invisible fields, that light itself is a ripple in that fabric, and that knowledge of these laws could unlock powers undreamed of. It is the story of how a quiet, thoughtful Scottish scientist working with pen and paper gave us the key to the modern world. Today, every flicker of a radio signal, every glow of a screen, every wireless connection, every beam of laser light, every X-ray image, all are monuments to Maxwell's vision. His pioneering contributions to electricity and magnetism did more than unify forces, they unified human understanding with the fabric of the cosmos. He gave us the ability to see beyond the visible, to hear across continents, to explore the universe in wavelengths our eyes cannot perceive. He showed us that the invisible forces shaping the world are not mysteries, but laws, elegant and knowable. And in doing so, he earned his place not merely as a great physicist, but as one of the true architects of modern civilization. When we look back at the great revolutions of science, there are rare moments when the language of the universe seems to shift, when the patterns of nature that once appeared fragmented suddenly reveal their unity. Such a moment occurred with the work of James Clerk Maxwell. His equations, born from the union of electricity, magnetism, and light, did more than describe phenomena, they became the very foundation of modern physics. They were not just formulas written on a page, but windows into the architecture of reality, equations so profound that they reshaped how we perceive the cosmos. To understand the significance of Maxwell's equations, one must remember the state of physics before him. Newton's mechanics reigned supreme, describing the motion of planets and projectiles with breathtaking precision. Matter was imagined as particles, forces as actions across space, and light as perhaps a wave in some invisible mechanical medium. Electricity and magnetism were fascinating but disjointed, governed by experimental laws rather than unifying theory. Coulomb had measured forces between charges, Ampere had charted the effects of currents, Faraday had drawn lines of force to illustrate fields, and Gauss had formulated theorems about flux. These pieces of knowledge were invaluable, but they remained scattered. Each was a tool in a toolbox, useful for its specific context, yet no single framework tied them together. Physics was powerful but compartmentalized. It was Maxwell who brought coherence. Between 1861 and 1865, he composed a mathematical symphony that wove together all that was known about electricity and magnetism, adding his own brilliant insight to complete the harmony. Out of this came what we now call Maxwell's equations, though in his lifetime they were spread across a far more elaborate structure. Later thinkers, most notably Oliver Heaviside, distilled his ideas into 4 concise equations that are taught today in every physics classroom. But no matter how they are expressed, their essence remains the same. They describe the behavior of electric and magnetic fields, their sources, and their interactions. The power of Maxwell's equations lies not only in their descriptive capacity, but in their predictive power. They explained phenomena that had been observed but not fully understood, and they predicted phenomena that had not yet been seen. In them, Maxwell found that a changing electric field could create a magnetic field, just as a changing magnetic field could create an electric one. From this symmetry emerged the possibility of self-sustaining waves, oscillations of electric and magnetic fields traveling through space. When Maxwell calculated the speed of these waves, he found it matched the measured speed of light. Thus, light itself was revealed as an electromagnetic wave. With this realization, the centuries-long mystery of light was resolved, and at the same time, The door was open to the vast electromagnetic spectrum beyond human sight. But the importance of Maxwell's equations went far deeper than explaining light. They marked a new way of doing physics. Before Maxwell, physics had largely been about forces acting between objects. After Maxwell, physics became about fields, entities that filled all of space, capable of carrying energy and momentum. The equations did not merely describe how charges pushed and pulled on each other. They described how the very fabric of space became imbued with invisible structures that guided motion and transmitted influence. In this sense, Maxwell's equations shifted the ontology of physics. The universe was no longer a collection of particles acting across empty void. It was a continuum, a field-laden cosmos, where reality was woven from invisible but mathematically precise patterns. This was not only a theoretical transformation. Maxwell's equations gave science a new kind of language, a language that combined empirical law with mathematical elegance. Each equation represented a principle. One showed how electric charges are sources of electric fields. Another described how magnetic poles do not exist in isolation, but always as dipoles, giving rise to magnetic fields with continuous lines. A third revealed how changing magnetic fields induce electric fields, capturing Faraday's law, and the final equation, uniquely Maxwell's own addition, introduced the displacement current. The idea that a changing electric field could generate a magnetic field, even in the absence of conduction currents. That single stroke completed the cycle and made electromagnetic waves possible. What makes this addition so extraordinary is the insight it required. At the time, there was no experimental demand for such a term. No instrument had detected it. Maxwell introduced it because he saw that without it, the equations would not be symmetrical or consistent. It was a leap of mathematical intuition, a demand that nature's laws must be harmonious. In trusting that symmetry, Maxwell discovered a reality no one had yet imagined. This was one of the clearest demonstrations in history that mathematics can reveal truths about nature even before they are observed. The implications for modern physics are staggering. Einstein himself once remarked that the work of Maxwell was the most profound and fruitful change in the physics of his time, perhaps since Newton. For Einstein, Maxwell's equations were not just useful, they were essential. They revealed the constancy of the speed of light, which became the cornerstone of special relativity. Einstein realized that if Maxwell's equations hold true, then the speed of light is the same for all observers, regardless of their motion. This led to a radical rethinking of space and time, fusing them into a single continuum, space-time. Without Maxwell, relativity might never have emerged, or at least not in the form we know today. Moreover, Maxwell's equations provided the framework for the development of quantum theory. The study of electromagnetic radiation, guided by Maxwell's field equations, eventually forced scientists to grapple with the dual nature of light as both wave and particle. The photoelectric effect, explained by Einstein, and the quantum theory of radiation, developed by Planck and others, all rested on the platform Maxwell had built. His equations were the classical foundation that quantum mechanics had to extend. The influence extends even further. Modern particle physics, with its gauge theories and quantum field theories, can trace its lineage back to Maxwell. His theory was the first field theory, the first to treat fields as entities with their own dynamics, independent of material sources. This concept is at the heart of the standard model of particle physics today. In many ways, Maxwell was the pioneer of the entire field, theoretic approach, the intellectual ancestor of our deepest theories of matter and energy. And yet, while Maxwell's equations are lofty in their significance, they are also practical. They underpin the technologies that define modern life. Every electric motor, every generator, every transformer, every circuit obeys them. Radio, television, radar, fiber optics, wireless communication, medical imaging, all are applications of Maxwell's insights. Engineers may not always reflect on the profound philosophy behind the equations they use, but every time they calculate a circuit or design an antenna, They are standing on Maxwell's shoulders. In the classroom, students often encounter Maxwell's equations as abstract formulas, perhaps intimidating in their compact mathematical form. But behind each symbol lies a story of discovery, of human curiosity translated into universal law. Each equation tells us something about the structure of the universe, something enduring and profound. Together, they are not merely tools of calculation, but expressions of unity, elegance, and depth. They remind us that the universe is not chaos but cosmos, ordered, harmonious, intelligible. Maxwell's genius was to see that unity. He stood at a crossroads of experiment and theory, intuition and mathematics, past knowledge and future possibility. By weaving together the threads of electricity, magnetism, and light, he created a fabric that has endured for more than a century and a half. His equations are timeless, as true today as when they were first written, as applicable to the workings of a smartphone as to the birth of a star. In this sense, Maxwell's equations are more than the foundation of modern physics. They are a symbol of what science can achieve. They show that with patience, imagination, and rigor, humanity can uncover the hidden patterns of the cosmos and write them in a form that is at once precise and beautiful. They stand as monuments to the marriage of thought and reality, proof that the human mind can capture the deep symmetries of nature in the language of mathematics. Maxwell himself did not live to see the full impact of his equations. He died in 1879 at the age of only 48, before Hertz confirmed the existence of electromagnetic waves, before Marconi sent signals across the Atlantic, before Einstein reshaped physics using Maxwell's framework. Yet his legacy endured and grew, spreading into every corner of modern science and technology. It is a reminder that ideas, once born, can outlive their creators, carrying forward into the future with ever-expanding influence. As one reflects on the story of Maxwell's equations, it becomes clear why they are regarded as the foundation of modern physics. They unified the forces of nature at a time when such unity seemed impossible. They reshaped our conception of reality, moving us from particles and forces to fields and waves. They opened the door to relativity, quantum mechanics, and field theory. They empowered the technologies that define our era. And they did all this through a set of mathematical statements so compact that they can be written on a single sheet of paper. There is a sense of awe in contemplating them, as if in those four equations lies the heartbeat of the universe itself. For behind the symbols are truths about the way the cosmos works, truths that remain unchanged whether on Earth or in the distant stars. To study Maxwell's equations is to glimpse the unity of creation, to feel the rhythm of fields that stretch across space and time, to hear, in the silence of mathematics, the music of the spheres translated into modern form. To speak of Maxwell's equations as the foundation of modern physics is not merely to recite formulas, but to trace the story of how these four elegant relations came to shape every branch of science. They are far more than symbols in a textbook. They are the rules by which the invisible threads of the universe weave themselves into patterns of light, force, and energy. Their beauty lies in their universality. Wherever there is a charge, a current, or a magnetic pole, Maxwell's equations apply. Wherever space stretches, they govern how fields propagate. And wherever humanity has sought to harness electricity or light, they have been the hidden guides. Imagine a universe without Maxwell's equations. There would be no understanding of how light travels, no way to predict the behavior of circuits, no grasp of why magnets interact, no explanation for wireless communication. Science would remain fragmented, stuck in partial laws and empirical rules with no deeper unity. It was Maxwell who gave us that unity, and in doing so, gave humanity both knowledge and power. His work was not the culmination of physics, but the launching point of modern physics, setting the stage for every revolution that followed. The true genius of these equations is not just that they explain known phenomena, but that they are generative. They point to realities beyond what is immediately visible. When Maxwell included the displacement current term in his formulation, he was correcting a gap in symmetry. Without that term, The mathematics did not balance. With it, the system became harmonious. Out of this harmony came the prediction of electromagnetic waves. It was as though, by insisting on beauty, Maxwell uncovered truth. That choice gave humanity radio, radar, television, satellites, the internet, and the entire age of wireless communication. But their influence went further still, into the heart of theoretical physics. The constancy of the speed of light implied by Maxwell's equations created a puzzle that only Einstein could resolve. If light travels at a fixed speed regardless of the observer's motion, then the structure of space and time themselves must be altered. The result was special relativity, which redefined not only light but matter, energy, and causality. In this way, Maxwell's equations were like a seed from which relativity grew. Einstein himself acknowledged this debt, remarking that the theory of electromagnetism was the most profound and influential achievement since Newton's Principia. From relativity, the influence spread to quantum physics, the study of blackbody radiation, the photoelectric effect, and the quantum nature of light all required confronting the electromagnetic field described by Maxwell. Light was both wave and particle, a duality that could only be reconciled through a new quantum theory. Even in quantum electrodynamics, one of the most precise theories in science, Maxwell's classical field equations serve as the foundation upon which the quantum corrections are built. Without them, the entire edifice of 20th century physics would lack its bedrock. This influence reached even into the quest to unify the fundamental forces. Maxwell had shown that electricity and magnetism, once thought separate, were in fact two aspects of the same force. This unification inspired later physicists to seek similar unions among the other forces of nature. Today, in the standard model of particle physics, the electromagnetic force is united with the weak nuclear force into what is known as the electroweak interaction. This achievement can be seen as a direct heir to Maxwell's vision, the pursuit of unity hidden beneath diversity. In this sense, his equations were the prototype of modern unification, setting the intellectual precedent for all later theories of grand unity. What is remarkable is how these equations straddle two worlds, the world of the practical and the world of the profound. On one hand, they describe everyday devices like electric motors, transformers, and circuits. Engineers rely on them to design power grids and communication systems. Without them, modern civilization as we know it could not function. On the other hand, they probe the deepest mysteries of the cosmos, explaining how stars shine, how galaxies emit radio waves, and how light travels across the vastness of interstellar space. They connect the practical light bulb in a room to the ancient starlight crossing billions of years to reach Earth. They are at once immediate and eternal. One of the striking features of Maxwell's equations is their elegance. In their modern form, they can be written in 4 compact expressions, each containing deep meaning. They are short enough to be inscribed on a monument, yet rich enough to underlie technologies, theories, and philosophies. This combination of brevity and depth has led many to call them among the most beautiful equations in all of science. Their symmetry, their balance, and their predictive power embody what many believe science should strive for: clarity, simplicity, and universality. Their role in shaping physics cannot be overstated. Consider the concept of the field itself. Before Maxwell, fields were at best a heuristic device, useful for thinking about forces but not regarded as real. After Maxwell, fields became the central players in physics. They carried energy, momentum, and information. They replaced the notion of instantaneous action at a distance with the idea of local interactions mediated through space. This conceptual shift was one of the most profound in the history of science, changing the way reality itself was imagined. In this sense, Maxwell's equations did not merely describe fields, they created the very concept of fields as fundamental elements of nature. From this conceptual revolution sprang the modern idea of field theories, which dominate physics today. Quantum electrodynamics, quantum chromodynamics, and the electroweak theory are all descendants of Maxwell's vision. Each describes fields with their own quanta. Each extends the idea that reality is a tapestry of interacting fields. It is no exaggeration to say that the structure of modern physics, its very architecture, is built upon Maxwell's foundation. Yet for all their theoretical weight, the human story behind these equations is equally compelling. Maxwell worked at a time when mathematics and experiment were drifting apart. Faraday was an experimenter of intuition and vision, sketching lines of force with no equations to back them. Maxwell was a mathematician who could translate those sketches into calculus, preserving their spirit while giving them form. He bridged two worlds, the world of hands-on experimentation and the world of mathematical abstraction. This marriage was not only fruitful but transformative. Without Faraday, there would have been no intuition of fields. Without Maxwell, no equations to make them rigorous. Their partnership across time is one of the great collaborations in science, even though they never truly worked side by side. Maxwell's own life was cut short at the age of 48, leaving the scientific world to wonder what more he might have achieved had he lived longer. He did not see Hertz prove the existence of electromagnetic waves. He did not see Marconi send signals across oceans. He did not see Einstein reshape space-time or Planck lay the foundations of quantum physics. And yet, through his equations, Maxwell was present in all these developments, his fingerprints on every advance. His work was not finished in his lifetime, but it was destined to shape all lifetimes after. Perhaps the most extraordinary aspect of Maxwell's equations is how they continue to yield new insights even today. Physicists use them to explore plasmas in fusion reactors, to analyze signals from distant galaxies, to design quantum communication systems. They remain as relevant in cutting-edge research as they were in the 19th century. This timelessness is the hallmark of foundational work. Just as Newton's laws still describe motion centuries after they were written, Maxwell's equations continue to guide our understanding of fields and waves. They are permanent fixtures in the landscape of science, impervious to the passing of time. If one stands back to consider the sweep of their influence, it is difficult not to feel awe. From the hum of an electric motor to the glow of a galaxy, from the radio in a pocket to the Wi-Fi signal streaming across a home, from the brilliance of Einstein's relativity to the intricacies of quantum field theory, Maxwell's equations lie beneath it all. They are the silent architecture of the modern world, written not in stone but in symbols, not in myths but in mathematics. They embody humanity's ability to perceive the invisible and to translate it into knowledge, knowledge that becomes power, and power that becomes civilization. In the end, Maxwell's equations are not only the foundation of modern physics, but a testament to the capacity of the human mind. They demonstrate that nature is intelligible, that the universe can be captured in patterns of thought, and that these patterns can be expressed in equations that remain true across centuries. They remind us that science is not just about collecting facts, but about seeing the connections that bind them into a whole. Maxwell saw those connections, and in doing so, he gave us more than equations. He gave us a vision of unity that continues to inspire. As long as light shines, as long as fields ripple through space, as long as humans seek to understand the world, Maxwell's equations will remain at the foundation. They are not relics of the 19th century, but living laws of the universe, as enduring as the cosmos itself. And in their enduring truth lies their greatest beauty. They are not just Maxwell's equations. They are nature's equations, the signature of a universe written in the language of mathematics, revealed by one man's extraordinary insight. When James Clerk Maxwell revealed through his equations that light itself was an electromagnetic wave, he did more than solve a mystery that had puzzled philosophers and scientists for centuries. He expanded humanity's vision of the universe. For thousands of years, light had been a subject of fascination and speculation. Ancient thinkers wondered if it was composed of particles streaming from luminous objects, or if it was some form of wave traveling through an invisible medium. Newton argued for a corpuscular theory, while Huygens championed a wave-like nature. Experiments in the 19th century, particularly those by Thomas Young and Augustin Fresnel, demonstrated that light behaved as a wave through its interference and diffraction patterns. Yet the question remained, what exactly was waving? Sound required air, water waves required liquid, but what carried the waves of light? Maxwell's equations provided the answer. In them, he saw that a changing electric field generates a magnetic field, and a changing magnetic field, in turn, generates an electric field. Together, they form a self-propagating wave that can travel through empty space. No medium was required. Light was not the vibration of some invisible ether, but an electromagnetic wave, a ripple in the electromagnetic field itself. This insight not only explained light's nature, but also placed it firmly within the domain of electricity and magnetism, unifying what had once been separate sciences into one. The revelation was astonishing. For centuries, light had seemed mysterious, unique, and almost otherworldly. By identifying it as an electromagnetic wave, Maxwell stripped it of its mystery and gave it a place within natural law. At the same time, he opened the possibility that there might exist other waves beyond visible light, other vibrations of the electromagnetic field that human eyes could not perceive. This speculation proved correct. In the decades that followed, scientists discovered radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays, all part of the same spectrum of which visible light was only a narrow band. The electromagnetic spectrum became one of the greatest legacies of Maxwell's theory, a hidden world suddenly revealed. Heinrich Hertz's experiments in the late 1880s provided the first confirmation of Maxwell's prediction by generating and detecting radio waves in the laboratory. What Maxwell had written as equations on paper became observable fact. From Hertz's work, practical applications quickly followed. Marconi developed wireless telegraphy using long waves to transmit signals across the Atlantic. Radio broadcasting was born, followed by radar, television, and countless other innovations. Each step was a direct unfolding of Maxwell's insight into the broader spectrum of electromagnetic radiation. But Maxwell's influence was not limited to technology. It extended to the very way we understand the universe. By recognizing light as electromagnetic, he provided the foundation for astrophysics. Astronomers no longer saw light from stars as a mysterious glow, but as waves carrying information about their sources. Through the study of the electromagnetic spectrum, scientists could probe the composition of stars, measure their temperatures, and even detect galaxies far beyond human sight. Today, the entire field of astronomy depends on this principle. Telescopes that observe radio waves, infrared light, X-rays, and gamma rays all rest on the framework Maxwell created. The universe is now studied not just in visible light, but across the full electromagnetic spectrum, revealing phenomena that would otherwise remain forever hidden. The discovery of X-rays in 1895 by Wilhelm Röntgen and the subsequent exploration of gamma rays and cosmic rays were natural extensions of Maxwell's vision. Though he did not live to see these discoveries, his equations had predicted the possibility of their existence. The recognition that invisible forms of radiation could penetrate matter, reveal structures inside the body, or provide images of distant cosmic events, demonstrated the transformative power of understanding light as part of a wider electromagnetic family. Medicine, communication, astronomy, and physics all found themselves revolutionized by a single conceptual leap. Maxwell's theory also reshaped philosophy. By showing that light is a wave in an electromagnetic field, he challenged the deeply rooted notion that light required a medium, the luminiferous ether, to travel. His equations worked perfectly without any ether, and though physicists initially resisted this implication, the famous Michelson-Morley experiment of 1887 later confirmed that no such medium existed. This realization prepared the way for Einstein's theory of relativity, which dispensed with the ether entirely and redefined space and time. In this sense, Maxwell's unification of light with electromagnetism was not only a triumph of physics, but also a profound shift in worldview. Perhaps the most enduring beauty of Maxwell's influence lies in its universality. Light, once regarded as a phenomenon apart, was revealed to be a natural expression of the same laws that govern electricity and magnetism. This unification was not merely theoretical but cosmic. It told us that the glow of a candle, the warmth of the sun, the invisible transmission of radio waves, and the deadly power of gamma rays are all variations of one phenomenon. It was a vision of unity in diversity, an example of how the complexity of the natural world can arise from a single underlying principle. Even today, Maxwell's influence on our understanding of light continues to guide new frontiers of science. The development of lasers, fiber optic communication, and quantum optics all rely on the electromagnetic nature of light. Modern imaging technologies, from MRI machines to satellite sensors, are applications of the broader spectrum. Space agencies build observatories to capture electromagnetic radiation at every wavelength, turning Maxwell's equations into tools for exploring the deepest mysteries of the cosmos. In the end, Maxwell's contribution to the study of light and the electromagnetic spectrum was nothing less than a redefinition of reality. He took one of the most familiar phenomena in human experience and showed that it was part of a vast, invisible ocean of waves, bound by laws of extraordinary elegance. By doing so, he gave humanity not just knowledge but vision, the ability to see beyond the limits of the eye, to hear the silent music of the universe in wavelengths both long and short, and to use that knowledge to transform life on Earth. His legacy is inscribed not only in physics textbooks, but in every radio signal, every medical X-ray, every telescope image of distant galaxies, and every beam of light that travels across the darkness of space. In the middle of the 19th century, physics was undergoing a transformation. Heat, once thought of as an invisible fluid called caloric, was beginning to be understood as energy, a manifestation of the microscopic motion of particles. Scientists like Rudolf Clausius and William Thomson, later Lord Kelvin, were establishing the laws of thermodynamics, formulating ideas about energy conservation and entropy. Yet the picture remained incomplete, because no one had yet found a way to connect the invisible world of atoms and molecules with the measurable, macroscopic behavior of gases and heat. It was James Clerk Maxwell who provided that crucial bridge, giving birth to statistical physics and opening the door to a new way of understanding the hidden motions of matter. Maxwell's entry into thermodynamics began with a fascination for gases. In his time, the behavior of gases was well documented through experiments. Robert Boyle had shown that pressure and volume were inversely related. Jacques Charles and Joseph Gay Lussac had demonstrated the link between volume and temperature. These gas laws provided reliable formulas, but they were descriptive rather than explanatory. Why should gases behave this way? What was happening on the microscopic scale to produce such simple relationships? Maxwell's genius lay in his ability to look beyond the surface, to imagine that the seemingly smooth behavior of gases was in fact the result of countless collisions among invisible, fast-moving molecules. In 1860, Maxwell published his groundbreaking paper on the distribution of molecular velocities in a gas. This work, known as the Maxwell-Boltzmann distribution after later extensions by Ludwig Boltzmann, revealed that the molecules of a gas do not all travel at the same speed. Instead, their velocities are spread over a range, with most clustered around an average value, but some moving slower and others much faster. This statistical picture was revolutionary, for it showed that the laws of thermodynamics could emerge from the collective behavior of millions upon millions of particles, each obeying the rules of Newtonian mechanics. By treating the gas as a vast ensemble of molecules, Maxwell shifted physics from the realm of exact prediction to that of probability. The implications were profound. Thermodynamics had always seemed deterministic, with fixed equations describing pressure, volume, and temperature. Maxwell demonstrated that beneath this order lay chaos, a world of ceaseless, random motion where certainty gave way to statistics. A single molecule could never be predicted with precision, but the behavior of the whole system could be known with remarkable accuracy. This was the essence of statistical mechanics, a framework that would eventually underpin not just thermodynamics, but the entire field of modern physics, including quantum theory. Maxwell's insight into molecular motion also explained why gases tend to spread out, why perfume fills a room, and why the atmosphere does not collapse to the ground. He showed that diffusion, viscosity, and thermal conductivity were natural consequences of molecules colliding and transferring energy. His calculations gave numerical values for these effects, linking microscopic theory with experimental measurement. Once again, Maxwell's work demonstrated the unity of nature. The familiar properties of gases were no longer mysterious, but the inevitable result of countless tiny impacts invisible to the naked eye. Among Maxwell's most famous contributions to thermodynamics was his thought experiment known as Maxwell's daemon. In 1867, he proposed a tiny, intelligent being capable of sorting molecules according to their speed. By opening and closing a microscopic door between two chambers, the daemon could allow only fast molecules to pass in one direction and slow molecules in the other, thereby creating a temperature difference without expending energy. This idea seemed to violate the second law of thermodynamics, which states that entropy or disorder must always increase in a closed system. Maxwell did not intend the daemon as a real machine, but as a way to probe the limits of thermodynamic laws and highlight the role of information in physical processes. More than a century later, his daemon would inspire profound discussions in physics, leading to modern connections between thermodynamics, computation, and information theory. Maxwell's statistical approach also influenced his contemporaries and successors in remarkable ways. Ludwig Boltzmann expanded Maxwell's velocity distribution and formulated a statistical definition of entropy, linking it to the number of possible microscopic configurations of a system. This step cemented the probabilistic nature of thermodynamics and gave deeper meaning to the concept of disorder. Later, Albert Einstein applied similar statistical reasoning to explain Brownian motion, providing crucial evidence for the existence of atoms. In each of these milestones, Maxwell's pioneering vision served as the foundation. It is difficult to overstate how radical Maxwell's contribution was in his time. Physics had long sought precise and exact descriptions of nature, from Newton's laws of motion to Kepler's laws of planetary orbits. Maxwell's statistical mechanics introduced a new philosophy, the recognition that certainty at the microscopic level was not always possible, and that probability itself was a fundamental tool for understanding the universe. This shift prepared the way for the probabilistic world of quantum mechanics in the 20th century, where uncertainty became a natural law rather than a limitation. The influence of Maxwell's thermodynamic work extended far beyond theory. By understanding the molecular basis of gases, scientists could design engines with greater efficiency, predict the behavior of chemical reactions, and study heat transfer with precision. His equations laid the groundwork for kinetic theory, which remains central to modern chemistry, engineering, and materials science. Every air conditioner, every combustion engine, and every model of planetary atmospheres carries echoes of Maxwell's vision. In reflecting on Maxwell's role in thermodynamics, one cannot help but admire the breadth of his mind. He was not content with unifying electricity and magnetism. He also sought to unify the microscopic and macroscopic worlds. His statistical physics revealed the hidden order in apparent randomness, the harmony within chaos. He showed that the invisible dance of molecules gives rise to the warmth of a fire, the movement of air, the pressure of steam, and the inevitability of entropy. Through him, the concept of energy gained deeper meaning, linked not only to motion and force, but to the very statistics of matter. Maxwell's legacy in thermodynamics endures because it touches both the practical and the philosophical. Practically, it explains the behavior of gases, supports engineering, and enables technologies. Philosophically, it challenges our notions of certainty, order, and predictability. It forces us to see the world as a complex interplay of countless unseen events, guided not by strict determinism but by probabilities and averages. In that vision lies a deeper truth about nature, one that has shaped physics ever since. By the time Maxwell passed away in 1879, his contributions to thermodynamics were already reshaping the scientific world. Today, his statistical view remains a cornerstone of modern science, influencing everything from quantum field theory to climate models. Just as his equations of electromagnetism revealed the hidden spectrum of waves beyond light, his thermodynamic insights revealed the hidden world of molecules beneath heat and pressure. In both realms, he expanded the horizon of human understanding, proving once more that he was not only the man behind modern physics, but also the architect of its deepest philosophies. In the long history of physics, few moments are as surprising as when a mind that has already revolutionized electricity, magnetism, and thermodynamics turns its attention to something as seemingly delicate and artistic as color. Yet James Clerk Maxwell was no ordinary physicist. For him, the study of nature's laws was not confined to forces and equations, but extended to perception, beauty, and the very act of seeing. His pioneering work on color vision and optics transformed the understanding of how humans perceive light, while laying the foundations of technologies that would one day shape photography, cinema, and digital imaging. In Maxwell's time, the mystery of color was unresolved. Artists knew how to mix pigments to create hues, and Newton had long before passed a beam of sunlight through a prism, revealing that white light is made up of many colors. But how exactly did the human eye process color? Why could a painter mix just a few pigments and yet reproduce the richness of nature's palette? And was there a scientific explanation for the way our minds combined sensations of light into the experience of color? These questions captivated Maxwell, who saw them not only as curiosities of perception, but as matters deeply tied to the physics of light itself. Building upon the ideas of Thomas Young, who had suggested that the eye might contain 3 types of receptors sensitive to different colors, Maxwell began systematic experiments in the 1850s. He designed ingenious devices to test how the eye perceives combinations of colored light. One of his methods involved using spinning color tops, discs painted with sectors of different colors that, when spun rapidly, blended into a single hue as perceived by the eye. By carefully adjusting the proportions of red, green, and blue sectors, Maxwell demonstrated that virtually any color could be reproduced through the combination of just these 3. This result was a powerful confirmation of the trichromatic theory of vision. The idea that the retina contains 3 kinds of receptors, each tuned to a different part of the spectrum, and that all our color experiences are built from their combined responses. Maxwell's experiments revealed more than a theoretical truth, they offered practical tools. He created quantitative charts of how different mixtures of primary colors produced particular shades, effectively mapping the mathematics of color perception. These charts laid the groundwork for colorimetry, the science of measuring and describing color in objective terms. To this day, modern color science rests upon principles that Maxwell helped to formalize. The televisions, computer screens, and smartphones that glow with vibrant hues are direct descendants of his discovery that red, green, and blue light are sufficient to recreate the spectrum of human vision. Perhaps the most striking moment in Maxwell's work on color came in 1861, when he produced what is widely regarded as the first color photograph. Using a ribbon of tartan cloth as his subject, he photographed it 3 times through red, green, and blue filters. By projecting the 3 filtered images through lanterns equipped with the same color filters and superimposing them on a screen, he recreated the original played pattern in color. Audiences at the time were astonished. For the first time, color had been captured and reproduced by scientific means. Though the process was crude compared to later photography, Maxwell's demonstration revealed a truth that would later shape the entire field of imaging, that color recording and reproduction could be achieved by separating and recombining the 3 primary color components. In this way, Maxwell not only explained color vision, but anticipated the methods behind modern photography, cinema, and digital displays. His work on color was not isolated from his interest in optics. Maxwell approached light with the same mathematical rigor he applied to electricity and magnetism, studying its properties as a wave and examining how it interacted with matter. He explored the polarization of light, the way its waves could be oriented in particular directions, and investigated how crystals and other materials could affect light's polarization. These studies were vital for the development of optical instruments and deepened the understanding of light's wave nature. Maxwell's attention to both the physical and perceptual aspects of light showed the breadth of his scientific imagination. He was equally at home calculating equations of the electromagnetic field and spinning color wheels to explore the mysteries of sight. The importance of Maxwell's contribution to color vision also lies in its human dimension. Physics often deals in abstractions, fields, forces, masses, but Maxwell's exploration of color connected science with the experience of everyday life. Every rainbow, every sunset, every brushstroke on a canvas was, in his framework, an interplay of three signals in the eye's receptors, translated by the brain into the rich tapestry of color. He demonstrated that beauty and science were not separate realms, but reflections of the same truth. By understanding how the eye perceives color, he provided a bridge between the physical world and human sensation. Later developments confirmed and expanded Maxwell's vision. Physiologists discovered the cones in the retina responsible for trichromatic vision, each sensitive to a different wavelength range corresponding roughly to red, green, and blue. Psychologists and engineers used his theories to design printing processes, color films, and television systems. The RGB model that dominates digital technology today, the same model that paints colors on computer monitors, phone screens, and LED displays, traces directly back to Maxwell's work. Every pixel lit in red, green, and blue is a tribute to his 19th century insight. Maxwell's explorations in optics also influenced the broader course of physics. By showing how perception was tied to physical laws, he foreshadowed the later interplay of physics and psychology in fields such as visual neuroscience and cognitive science. Moreover, his insistence on precise, quantitative methods in studying color helped establish the experimental discipline of psychophysics, which measures the relationship between physical stimuli and sensory responses. In this sense, Maxwell was a pioneer not only of physics but of modern perceptual science. What makes his work on color vision remarkable is not just the elegance of his experiments, but the way it reflects the unity of his mind. Maxwell did not see a divide between abstract theory and concrete experience. For him, understanding the invisible waves of electromagnetism and the visible hues of a tartan ribbon were part of the same pursuit, uncovering the laws that bind together nature and perception. His scientific vision was holistic, embracing the mathematical and the aesthetic, the microscopic and the macroscopic, the theoretical and the sensory. By the time Maxwell's life came to an end in 1879, his achievements in color vision were already influencing both science and art. Painters and photographers began to see new possibilities in reproducing the natural world. Engineers and inventors glimpsed the future of imaging, and physicists recognized that the study of light and perception was not a minor curiosity, but an essential part of the larger story of waves and fields. Today, whenever a photograph captures the exact hue of a sunset, whenever a screen renders the vivid green of a forest or the deep blue of an ocean, Maxwell's legacy is present. Maxwell's contribution to color vision and optics reminds us that physics is not only about forces and particles, but about understanding how humans experience the universe. His work showed that the laws of light extend into the very act of seeing, and that perception itself can be explained by the language of science. In revealing the mechanics of color, he gave humanity not just a deeper grasp of physics, but also a greater appreciation of beauty, proving that in the harmony of science and art lies the true power of knowledge. James Clerk Maxwell did not live to see the 20th century, but the seeds he planted shaped its greatest revolutions. His death in 1879 came just as physics was preparing to move into entirely new realms, yet his equations and his vision guided the hands of those who would redefine space, time, and matter itself. If Newton's Principia had been the cornerstone of classical mechanics, Maxwell's electromagnetic theory was the bridge that carried science into the modern age, influencing Einstein's relativity, the rise of quantum theory, and the vast technological landscape that defines contemporary life. His legacy is not simply one of brilliant discoveries, but of transformation, for he changed the way humanity thinks about the universe. When Maxwell first wrote down his equations, he probably did not realize just how far their consequences would reach. They described electricity and magnetism as one, and they revealed light as an electromagnetic wave. But buried within them was something deeper, the prediction that electromagnetic waves travel at a fixed speed, independent of the source. That constant, the speed of light, would later become the cornerstone of Albert Einstein's special theory of relativity. Before Einstein, physicists wrestled with the problem of the luminiferous ether, an imagined medium through which light waves supposedly moved. Experiments, most famously the Michelson-Morley experiment of 1887, failed to detect this ether, leaving a paradox unresolved. It was Einstein who in 1905 cut through the puzzle, declaring that Maxwell's equations made sense only if the speed of light was absolute, and that space and time themselves must adjust to preserve this truth. Without Maxwell, relativity would never have been born. Einstein himself acknowledged this debt, often stating that his special relativity was built upon the foundation Maxwell had laid. Maxwell had revealed a universe in which light was not just a phenomenon, but a universal constant, a limit woven into the very fabric of reality. Space and time could bend, mass and energy could transform, but the speed of light remained fixed, just as Maxwell's mathematics had implied. In this way, Maxwell's unification of electricity and magnetism became the launch point for Einstein's unification of space and time. But Maxwell's influence did not stop at relativity. His statistical approach to thermodynamics, his use of probability in describing molecular motion, anticipated the logic that would become essential in quantum theory. When Niels Bohr constructed his model of the atom in 1913, explaining electrons orbiting a nucleus with energy levels tied to radiation, he relied on electromagnetic principles that traced back to Maxwell. Later, when quantum electrodynamics emerged in the 20th century, blending quantum mechanics with the theory of fields, physicists once again turned to Maxwell's framework. The equations that described photons, the quanta of light, were direct descendants of the classical waves Maxwell had envisioned. In many ways, quantum theory can be seen as the child of Maxwell's vision and the heir to his unification. He had shown that fields could be as real as particles, that invisible forces filled space and shaped matter. Quantum mechanics would take this further, revealing that particles themselves were waves, that probabilities replaced certainties, and that light could behave both as a wave and a particle. Maxwell had not foreseen this duality, but his equations had opened the door to it. They were the first great field theory, and quantum field theory was their natural evolution. Every photon detected in a laboratory, every laser beam, every particle interaction studied in a collider still echoes with Maxwell's insight that the universe is woven together by fields. Beyond relativity and quantum mechanics, Maxwell's legacy lies in the sheer universality of his ideas. He did not simply describe a phenomenon, he created a language. His equations became the grammar of modern physics, a system so elegant that physicists continue to marvel at their simplicity and depth. They inspired generations of scientists to search for unification, to seek deeper laws that bind the forces of nature together. Einstein's later dream of a unified field theory, though never fulfilled, was in many ways a continuation of Maxwell's own vision, that the diverse phenomena of the world could be traced back to a single harmonious framework. The influence of Maxwell also stretches into technology in ways he could scarcely have imagined. His equations predicted the existence of radio waves, and within decades, Hertz and Marconi turned that prediction into wireless communication. From there flowed radio, television, radar, satellites, and the global networks of today. Every mobile phone call, every Wi-Fi signal, every transmission from space probes depends on the electromagnetic principles he revealed. Likewise, his work on optics and color vision shaped the development of cameras, cinema, and digital imaging. His statistical mechanics influenced modern chemistry and material science, while his thermodynamic insights underlay engines, refrigeration, and countless machines. Maxwell's legacy is not confined to physics but extends into every corner of human experience. Philosophically, his work transformed how humanity perceives the universe. Newton's cosmos was a clockwork of particles and forces, precise and mechanical. Maxwell's universe was one of fields and waves, invisible structures binding space together. This vision prepared minds for the more radical revolutions of the 20th century, where relativity bent time and quantum mechanics dissolved certainty. He demonstrated that mathematics could reveal realities beyond human senses, that beauty and symmetry in equations were not merely abstract, but reflections of physical truth. His legacy is thus both scientific and philosophical, shaping not only discoveries, but the way we imagine nature itself. Maxwell's enduring impact can also be measured in the reverence scientists hold for him. Richard Feynman once remarked that from a long view of history, the greatest change in physics came from Maxwell's discovery of electromagnetic waves. Einstein himself described Maxwell's work as the most profound and most fruitful that physics had experienced since Newton. Such praise is not given lightly. It reflects the recognition that Maxwell's contributions did not merely solve problems of his day, but charted the course of the entire scientific century that followed. Even today, Maxwell's equations continue to guide exploration at the frontiers of science. In astrophysics, they describe how light travels across cosmic distances, carrying information from galaxies billions of years old. In engineering, they govern the design of antennas, circuits, and optical fibers. In medicine, they underpin imaging technologies from X-rays to MRI scans. In particle physics, they serve as the template for gauge theories, the mathematical structures that describe fundamental forces. His vision resonates in the deepest questions still asked today: how can the forces of nature be unified? What lies beyond the standard model? And how do quantum fields weave together space, time, and matter? James Clerk Maxwell's life was brief, but his legacy is eternal. He died at the age of only 48 before he could witness the revolutions his ideas would inspire. Yet through relativity, through quantum theory, through every technology that transmits a signal or bends a wave of light, his presence endures. He was the man behind modern physics not because he closed a chapter, but because he opened a new one still being written. His equations remain etched in the very fabric of reality, a reminder that the universe speaks in a language of harmony, and that those who listen closely can glimpse the profound unity of all things.